Hello everyone. The topic I'm going to take today is fluid dynamics, and it is one of the most important topic. And important is because we will be dealing with the Bernoulli equation, and it is one of the most important equation in fluid mechanics entire. Uh, because honestly speaking, if you know how to apply the Bernoulli equation, you know how to solve question in fluid mechanics, entire fluid mechanics, as well as dynamics. So today we will be discussing mainly about the Bernoulli equation and its application, uh, because in the past recent years, many of the questions are being asked from the Bernoulli equation. So let's start. This will be the flow of the presentation. First of all, we will be dealing with the continuity equation, then Bernoulli equation, its assumption, then its application part, Venturi meter, orifice meter, because many of the time question are being asked from the Venturi meter also, orifice meter also. All right, so let's start. So what is continuity equation? Continuity equation is this. Suppose there is a pipe. You can see this pipe. This is a pipe, and there is a fluid entering at velocity v1, and there is an exit velocity of v2 of v2. Here the cross-sectional area is A1. Here the cross-sectional area is A2. So as simple as that, the continuity equation says that the mass of the fluid entering at section 1 will be equal to the mass of the fluid which is taking exit from section 2. So if in a fluid in a streamline flow and it is incompressible, then we can say that the mass of the fluid passing through different cross section are equal. Simple. All right. So the mass remains the same. So this is common sense also. The amount of fluid which is entering at this section will be equal to the amount of fluid which is taking exit from this section. All right. Here the word incompressible. Incompressible means the density remain constant. Density remain constant. All right. Compressible means that the density may vary, but in the entire study take we consider that our fluid to be incompressible because it's an assumption. Basically it helps to solve most of the question in a easy way. So water is also incompressible, and in fluid mechanics mainly we deal with water and sometimes with gases also. So basically we treat most of the fluid as incompressible, that is the density remain constant, right? Then what is the mass flow rate? Since we know density is equal to mass upon volume, then mass is equal to density into volume. All right. So we can write density into volume at section 1 at this section will be equal to density rho 2 into V2 at this section. Here V is not volume, sorry, here V is not velocity, it is the volume flow rate. In fluid mechanics, what is V? Basically, we treat as V is volume flow rate. Volume flow rate. Or we can also say it as discharge. Hold on for a second, please. Yes, we can say it as volume flow rate or discharge. And its unit is meter cube per second. And what is discharge? You can see the amount of fluid which is flowing, or the volume of fluid which is flowing per second. All right. Rate, in terms of time we are talking, the amount of fluid which is entering or leaving the section in per second. So we can also say this is a discharge Q, and we can also write that discharge Q is equal to area into velocity. How? See, area is unit is meter square, velocity. Here V is velocity, V is meter per second. So meter cube per second. You can say the unit is same. So discharge Q is equal to area into velocity. So in short, the discharge remains constant at section, both at this section and at this section. The discharge remain constant. So yes. So we can write this volume flow rate is A1 into V1. And what is A1 V1? Is discharge area into velocity. Remember that this is important. Then rho 2. Then this volume flow rate is A2 into V2. And I have already said in our study we have assumed that the fluid remain incompressible, that the density remain constant. So here rho 1 is equal to rho 2. We can write A1 V1. We can write A1 V1 is equal to A2. This is the continuity equation. Remember this. This is very important. Now, so the mass of the liquid inside the container remains the same. Rate of mass entering is equal to rate of mass leaving. Rate of mass entering, I have already told, rho A1 V1. A1 V1 is basically discharge. Rho A2 V2. They have taken simply rho because I have already said for an incompressible fluid, density remain constant. Then this equation is known as continuity equation, and it is one of the most important equation. You have to remember this because it is applied during the Bernoulli equation also. All right. I hope this is simple and clear. So let's move forward. This is Bernoulli principle. What is Bernoulli principle? Basically deals. Okay, this continuity equation deals with the conservation of mass. That the mass remain constant. All right. And what is Bernoulli principle? Bernoulli principle is basically the conservation of energy. Conservation of energy. Total mechanical energy. Total mechanical energy is basically the sum of gravitational potential energy, kinetic energy, and pressure energy. So Bernoulli simply says that the entire energy, that is the conservation due to the conservation of energy, that the entire energy of the fluid at section 1 and at section 2 remains the same. So I can read the total mechanical energy of a moving fluid comprising the gravitational potential energy of elevation, the energy associated with the fluid pressure, and the kinetic energy of the fluid motion remains constant. Right? Okay. What is this fluid pressure energy? Remember this. Okay. Suppose this is a pump and uh, it is installed at the ground floor, at the ground floor, and it is supplying fluid to a height h to a tank. This is the tank placed at the roof of the house. All right. So how will this flow take place? We know the flow take place when there is del P, pressure difference, isn't it? Without pressure difference, there will be no flow. All right. Without pressure difference, there will be no flow. Suppose at pressure at the pump, we are supplying pressure P1, and at due to pressure difference, due to change in pressure, due to pressure P1 and P2, there is a head which we are getting. There is a flow rate which we are getting. All right. So basically, in terms of head, we will write H is equal to P upon rho G. Remember this thing. Or we have studied it. Might have studied pressure is equal to rho G H, isn't it? Suppose there's a big tank and it is filled with a fluid at a depth h. At a depth h, the pressure which is felt here will be rho G H. Will be rho G H. So obviously we feel pressure when we enter into a fluid. All right. When we enter into fluid, we feel pressure. That's the reason we feel pressure. All right. The pressure is equal to rho gh. In terms of head, h is equal to p upon rho g. So in fluid mechanics, we mainly deal with the head. Head is basically the height in meter or centimeter. Mainly we take with meter. So it's basically the height which is the which is caused due to the pressure difference. So remember this thing also, P upon rho g. This is the head due to pressure difference. Head due to pressure difference. In this case, we can write P1 minus P2 upon rho g is equal to H. Here rho is the density, g is the gravity, and P1 and P2 are the pressure difference. So if you want to make a flow from one point to another point at a height h, then this formula is used, P1 minus P2 upon rho g, because without pressure difference there will be no flow. All right. So this was simply the basic pressure energy which we were talking about. Then kinetic energy, you already know, it's half mv square. All right. Kinetic energy is half mv square, and the potential energy. Suppose you might have studied in class 9th and 10th. Suppose there's a ball m at a height h. The potential energy of the ball will be mgh, mass into gravity into height. All right. So basically, only the first one which I explained, that is head, p upon rho g. This is due to fluid pressure. Then another form of energy which is due to the flow velocity is kinetic energy, which is half mv square. And the third form of energy is the potential energy, that is mgh. The summation of all these energy is basically what? Constant. This is what the Bernoulli says, right? So in standard form, I can write, remember this equation. We will apply this equation only in terms of head. Suppose there is a section 1 and section 2, P upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. This this is basically pressure energy, this is kinetic energy, and this is the energy associated with the potential energy, that is the head, datum head. Again, the same thing, and this is basically the Bernoulli equation. You need to remember this in this form only. Now we will be deriving the Bernoulli equation. All right. Before actually moving to the derivation, we should see the assumption involved in the Bernoulli equation. First of all, the fluid is ideal, that is the viscosity and the surface tension is zero. What is surface tension and viscosity? I hope you already know. Viscosity is basically the resistance between the layers, all right? And surface tension is, suppose this is a tank and there are many fluid particles here, all right? The Suppose this is the particle which is present at the topmost layer. Now, this particle will be experiencing the fluid pressure in all the direction. This also in all the direction. But this particle will be experiencing the fluid pressure in the downward direction only. Since there is no upper layer above this, so this portion remain empty due to fluid pressure. So basically, this molecule will be experiencing only the downward fluid motion, and there will be no, since there is no fluid available uh, above this. So due to this, there's this particle will be absorbing the surface tension, the tension which is available at the surface. Simple. That is surface tension. So we considered is fluid as ideal, that is the surface tension is zero. We are assuming that the entire fluid is experiencing the uniform pressure, right? So surface tension is zero. Fluid is irrotational. Two type of fluid, rotational and irrotational. Suppose this is the fluid, and if it is moving with respect to its own periphery, all right. Now see in this way, then in this way, this is basically rotational. Irrotational is the fluid is not moving with respect to its own position. So we in Bernoulli equation we treat fluid as irrotational and incompressible. Incompressible means the density remain constant. All right. This is important. Most of the time the question are being framed from the assumption part also. The fluid is steady and continuous. What is steady? Steady means that the fluid is not changing its properties with respect to time. With respect to time. For example, the fluid velocity del V by del T is constant with respect to time. Fluid acceleration is also constant with respect to time. So, in respect to time, if the fluid is steady, its properties are not changing with respect to time, it is referred to as steady and continuous. Fluid is along the streamline, that is one dimensional. The velocity is uniform, okay, equal to mean velocity. The only forces acting on the fluid are the gravity and the pressure forces. This is important. The forces acting on the fluid are only gravity and pressure forces that are acting on the fluid. I hope the assumptions are clear. First of all, the fluid is ideal. There is no viscosity, no surface tension, incompressible, that is the density remain constant, steady, that is it is not changing its property with respect to time, streamlined, that it is flowing in one dimensional, and the forces which are acting are basically the gravity and the pressure forces, right? So let's see a quick recap of the derivation part. So consider a pipe with varying diameter, height through which cross-sectional area A, velocity V, ground Y, pressure P at both the point. So consider this section at section 1 and this section at section 2. At section 1, this is the area A1 and the fluid is flowing with the velocity V1. At section 2, there is a velocity V2 and the area is A2. You can see from the this is the flow and the distance from the datum from this fluid line is Y1, or we can say it's Z1 also, and for this part of the fluid is basically Y2 Z2, or we can say it's Z2. All right. So due to the velocity V1 and at area A1, there will be the force acting at this element due to pressure, right? So suppose this is the P1 pressure acting here. So pressure is equal to what? Force upon area. So F is P1 A1 acting at section 1 and force F2 is P2 A2 at section 2. Since we know work done is equal to force into displacement, and displacement is dx1 for this part and dx2 for another part. Dx is basically we will integrate the entire equation to work done. And so from the work energy principle, we also know that work done is equal to del Ke change in kinetic energy. Change in kinetic energy. Work done. That is F into D is equal to change in kinetic energy half m V2 square minus V1 square. So you can see this also density incompressible. Work done is force into displacement F1 dx. This is minus sign because in direction force is acting in this direction and F2 is acting in this direction. So due to opposite direction, the sign is minus. Work done, force is pressure. Pressure is force upon area. We have put the value of force P1 A1. Now, yes, area into this dxn is basically dv. This is the uh, change in volume p1 minus p2 into dv. Then change in kinetic energy, work done is equal to change in kinetic energy. We will equate this, and from the energy equation also there is potential energy due to the height. Due to these height, there will be the potential energy, kinetic energy, and pressure energy. So all these energy we need to conserve. The work done is equal to summation of kinetic energy and potential energy. We'll put the values and this rearranging system we will get P1. This is basically the Bernoulli equation. This is the pressure energy P1 due to the pressure difference P1 P2. This is the kinetic energy due to the flow velocity, and this is basically the potential energy due to the height difference. So you can remember this also, but I recommend you to remember this equation in this form P1 upon OG plus V1 square upon 2G plus Z1 equal to P2 upon rho G plus V2 square upon 2G plus Z. Right. In this way, it is easier to solve question. Once I will be solving question in the later part of the video, then you will understand. So this is basically the Bernoulli equation. You don't need to remember the entire derivation part, but simply remember this. But you should know the conservation of three forms of energy are taking place: pressure, kinetic, and datum or potential energy. So now we will learn how to apply this equation, how to apply this Bernoulli equation, because you can say three terms are in left side, three terms are in right side. So applying this equation become cumbersome, difficult if we have the end, if we don't have many values. So we basically what we do is we try to eliminate most of the values depending upon the situation. So we will be applying the Bernoulli equation in this tank portion. In the above figure, calculate the velocity at f flex A2. At we need to calculate the velocity V2. All right. So consider this as section 1 and this as section, or you can say this as section 2, because here the velocity, the area is also A2. So we are applying Bernoulli equation at point 1 and 2. P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus of Z. All right. So let us consider this is the datum. This is basically your baseline. From baseline, this height is basically 0, since this is the baseline, and this height consider at Z1, which is equal to h at section. All right. Also, here the velocity will be V1. Then further, in fluid mechanics, pressure is very important. I know but here the pressure will be 0. See, this is basically what is, since this is open to the atmosphere, so there will be acting the atmospheric pressure. And in fluid mechanics, if we calculate in terms of gauge pressure, we take atmospheric pressure to be 0. Further, at the exit of this tank, the pressure is also here. P2 is also atmospheric, isn't it? So here P2 is also 0. We consider it to be 0. All right, because we are talking in terms of gauge pressure. All right, the pressure, atmospheric pressure is acting at this portion. Since after exit there will be fluid will be flowing in an open area. This is also the atmospheric pressure. So P1 is also 0, P2 is also 0, since they are open to this. So I already told you before that before applying Bernoulli equation, we need to see the terms, how we can eliminate, so that it is easier for us to calculate the questions. All right. So in the earlier part also I told you, if you know how to apply Bernoulli equation, you know how to solve question in fluid mechanics. So I will be telling you the tips and tricks. Then P1 is 0, P2 is 0. Since this V1 is also 0. Why? V1 is 0 because V1 is 0 because since this is a big tank, for example. This is a very big tank. If you are opening if you are opening this portion, the velocity V2, you will see some form of velocity V2, but this level will come very, very slowly, isn't it? Because it's a very big tank. You weren't able to, you weren't able to differentiate that this tank is going down. It will be going very slowly, at very, very slowly. At it will take very high time so that you will see this level to be at this level. So in simple, in a very big tank, we considered velocity at the upper portion of the tank to be 0, because this velocity will come very, very slowly downward. All right. And you can say the velocity V2 will be more because here area is less. I hope this is clear. Here Z1 is equal to H. From the datum, Z2 is 0 and Z1 is H. H is equal to V2 is 0, atmospheric, V2 square upon 2g. Z2 is also 0 since it is from datum. So V2 square is equal to 2gh. V2 is equal to, taking root on both sides, is root 2g. V2 is equal to root of 2g. In this way, you have to calculate the question. So for a big tank, if you know this height, you can easily calculate this velocity. V2 is root 2gh, where g is the gravity, h is the height. Simple. I hope you understand this. So we will be solving question in the later part, previous year question from this Bernoulli equation. Before that, we should move toward the application part, venturimeter. This is the application part of the Bernoulli equation, one of the most important device which is used for the measuring of the rate of fluid, which is used for the measuring of the rate of fluid. What is the amount of fluid which is flowing through the pipe? Because in many of the, this is important in the medical line also, in the industries, chemical industries also, we should know, no, how much amount of fluid is, how much chemical we are transporting from one portion to another, or what is the amount of blood which is flowing in the veins of a patient, and all those stuff. So basically the rate of fluid, what is the amount of fluid we need to enter, is important, because it plays a crucial role in industry. So the venturimeter consists of three parts: the converging zone, the throat diameter, and the divergence. In the converging zone, converging, as the name suggests, the area is decreasing. All right. The throat diameter, it is the smallest diameter. Here, area is constant. Diverging zone is the zone where area is increasing. All right. See, this is venturimeter. See, mm, this is the converging zone. All right. This is the throat portion. Here you can see the this diameter. This diameter remain constant. Here the diameter is decreasing, or the area is decreasing, and this is the diverging zone. Here the area is increasing, or the diameter is. So it works on the Bernoulli equation and the Bernoulli principle. How it works and why we have made the this venturimeter like this is because, when there is a change in area, due to change in area there is a pressure difference, and the fluid will not be flowing, I already told you, without the pressure difference. So here area is, pressure is P1, here pressure is P2. Why there is a pressure difference? Because of the area difference. Here suppose the diameter is D1, and here at this portion the diameter is D2. So we can consider this section as section 1, C section 1, this is section 2, and we will be applying the Bernoulli equation between these two portion 1 and 2. Alright. Due to the pressure difference, what happens is we have also connected one manometer. What is manometer? Manometer, I think you have already studied earlier also. Manometer is basically used to measure the pressure difference. Alright, I have said this is the pressure difference, but how will we come to know that what is the amount of pressure difference? So this is basically the device which is used to measure the pressure difference. Manometer. There are many type of manometer, inverted. I hope you YouTube. This is YouTube type. You can see this is YouTube type. And what happens is there's one fluid which is basically mercury. Which is mercury. Which is why mercury? Because the mercury has the high density, and other is the flowing fluid. In this case, I think we are treating as water. This is water, and this is the mercury. So basically, due to the pressure difference, there is a height h, which is the difference due to the, which is this height is basically due to the pressure difference at P1 and P2. If we know this height, we can know the pressure difference, and vice versa. If we know the pressure difference, we can know the height. All right. So we will be applying the Bernoulli equation at section 1 and section 2. So let's start. P1 upon rho g. Again the same equation. Remember this by heart, this equation. P2 upon rho g. plus V2 square upon 2G plus of Z2. Now, as I said you, Bernoulli equation is important, but we should know how to apply, what terms need to be cancelled out. Since we can see at this portion, this is the datum, Z1 is equal to Z2, because from the center line, this is the same distance. So we can easily cancel Z1 and Z2. Alright. Now, P1 upon rho G plus V1 square upon 2G equal to P2 upon rho G plus V2 square upon P. We can rearrange the term, bring this P2 here. This P1 minus P2 upon rho G is equal to 1 upon 2G. P1 here this side, V2 square minus of V1 square. So in the initial phase, I already, before starting this lecture, I told you that due to the pressure difference, we can know the height. And how will we will know the height? Due to this mercury column and the exact H. This is basically H. This height is due to the pressure difference divided upon rho into gravity. We can know the height V2 square minus V1. I already told you my first slide, I think. Yes. Mm, I think I have erased that particular part. Yes. So suppose there is not only in this case, in case of pipe, even I have given the example earlier of this pump and this tank. If this height, it, here pressure is P1, pressure is P2. If we want to know this height, we can divide by P1 minus P2 upon rho G. We can easily know the height up to which the water is being raised. Water is being raised. So H is basically the height of this manometer column at this height. So we can term this equation as equation 1 now. Now since we have the another equation, continuity equation, as earlier I told that the amount of fluid which is entering at this section will be equal to amount of fluid which is leaving at section 2. So A1 V1 is equal to A2 V2. You can also write this. So V1 V2 square. We can rearrange this equation more. You can write 1 upon 2G. You take out V1 square common. V1 square common. So we can write V2 upon V1 whole square minus 1. Can we write this way? Are you able to understand? Can you understand this? Alright. See this equation. 1 upon 2G V2 square minus of V1 square. If we are taking V1 square common, or we can say we are dividing this by V2, V1 square as common, V2 upon V1 whole square minus of 1. If you solve this equation, you will get this equation back. Alright. Whenever you find confusion in the derivation part, obviously they are not being asked in GATE, but eventually mm, in many of the places they may ask the derivation part in semester exams also. So the easiest thing is to solve this equation again, and if you're getting the same equation above, then you're right. Alright. So you can cross check it. 1 upon 2G V1 square. We are taking common. Multiply this V2 square minus V1 square as it is. V1 square cancel. You are getting the same equation. So I have rearranged this equation in this form. Sorry, 1 upon 2G. This equation. We'll be using it. Alright, this is the height. So simply we have applied the Bernoulli equation between point 1 and 2. We have cancelled out the Z1 and Z2, and P1 minus P2 is basically the head in the manometric tube, and we have rearranged this term as like this. Now, we can put V2 by V1. Since see, this is V2 by V1, we can write V2 by V1 as A1 by A2, isn't it? And what we were getting, H is equal to 1 upon 2G V1 square, V2 upon V1 whole square minus of 1. Alright. Then this V2 by V1, we can put this value here. H is equal to 1 upon 2G V1 square. V2 by V1 is basically A1 upon A2 whole square minus of 1. We can solve it, we can find the value of V1. So V1 is H is equal to 1 upon 2G V1 square. A1, solve this bracket part, A1 square minus A2 square upon A1 square. Then V1, how we can find the value of V1? V1 square is equal to 2GH into A1 square upon divided by this value. I hope you are understanding because simply I'm rearranging the terms. For V1, we will be taking the square root on both sides. So this will be root 2GH. Square root of A1 square is A1 upon root of A1 square minus of A2. So this is the value of what? V1. This is the value of V1. Now discharge Q is equal to area into velocity. I already told you this is the volume flow rate. So discharge Q is equal to A1 V1, which is equal to A2 V2. Both are same because this A1 will be small or A2 will be small. This will compensate all because this value will be A1 V1 is equal to A2 V2. Since we have calculated V1, we will find we will put A1 here. Discharge Q is equal to A1 into V1. We will put this value, which is root 2GH. I think I have committed some mistake. H1 upon 2G V1 A1 2 square. Yes. See this part. This A1, this part A1 square minus A2 square here will be A2 square. Will be A2 square. Sorry. So A1 into V1. V1 is root 2GH A2 on root of A1 square minus of A2 square. So can write it as A1 A2 root of 2GH on root of A1 square minus of A2 square. So this is your discharge through the venturimeter. So simple, this is area A1, this is area A2. If we know A1 and A2 and this height H, this height we can know from the pressure difference P1 and P2. All right. So in question, if they have given the pressure difference, you can easily find this height. Even in A2, they will give you most of the time. Even in A2, then simply you can find the discharge or the flow rate. Discharge or the flow rate from the venturimeter. One more thing, this discharge is basically the actual discharge, uh, basically the ideal discharge. During the flow, there will be some form of losses in pipe. So to account for this, we have one factor. This is CD, which is known as coefficient of discharge. Coefficient of discharge. This account for the loss of the flow fluid, or there's some form of fluid will be will be attaching towards the pipeline also. There will be some losses also. So this is basically the coefficient of discharge, which is the ratio of actual discharge, actual discharge to the theoretical discharge, to the theoretical discharge, CD. So we can also add this factor here, CD. This is the coefficient of discharge, and its value is always be less than 1, obviously, because actual discharge will be less than the theoretical discharge. So obviously this value will be less than 1. So this is the discharge through the venturimeter. You don't need to remember the entire derivation part, but this formula is very important. You have to remember this and how we have calculated this P1 minus P2 upon rho g, because because gate always play with the concepts. So they may give you the pressure at 2 points and you don't know H, and then you have to find the um, this value, the discharge of the flow rate through the venturimeter. All right. Then we have another instrument, orifice meter, which is very much similar to the venturimeter, orifice meter. Only what we have is there is a flat circular plate. We have flat circular plate at this position. Here is also converging portion. You can treat it as throat, and there is also diverging portion. And due to this converging portion, there is vena contracta form. Vena contracta is basically the change in the cross section from higher value to lower value, and its value is Cc. We can say is coefficient of contraction. Coefficient of Cc is coefficient of contraction. In venturimeter, it was coefficient of discharge. Coefficient of contraction. Here, Cc is basically the area at this vena contra, AC, on A naught is basically the higher one area. Right. For example, uh, this area is A naught and this area is AC. So the ratio of these both area is coefficient of contraction, and the formula remains the same. Formula remains the same for orifice meter also, which is Q is equal to CD. Sorry, A1 A2 root of 2GH root of A1 square upon A2 square. This formula remains same for orifice meter as well, because it works on the same principle, and we will be applying the Bernoulli equation in this case also. So I'm not deriving this part because it is not important from the gate point of view. So you need to simply remember the formula. All right. Then we have one small topic. This is the relation between different coefficient. CD is equal to CC into CV. Remember, this is important. CD is coefficient of discharge, CC is coefficient of contraction, CV is coefficient of velocity. Coefficient of velocity. All right. So remember this coefficient of discharge, CD is equal to CC into CV. This is also being used in between the numerical portion also. So what we have studied is, let me give you a brief recap so we can move towards the question. First of all is the continuity equation, continuity principle or equation. What is A1 V1 is equal to A2 V2, or the mass flow rate remains same for two section in a pipe flow. Remember this area, we know is simple, pi by 4 of d square, or you can use pi r square whatsoever. I use this because in fluid mechanics most of the time the units are given in terms of diameter, so you can use this pi by 4 into d square. Velocity, meter per second. Then we have another equation, was the Bernoulli principle. What was it? That the entire it depends on the conservation of energy, entire pressure energy, kinetic energy, and the uh, potential energy remain constant within a fluid through the pipe. So P, pressure energy, P upon rho g, plus kinetic energy, V1 square upon 2g, plus Z1 is equal to P2 upon rho g, plus V2 square upon 2g, plus of Z2. Actually, this equation, why I am writing this equation, because it is this equation is denoted in terms of head. Head means the distance, meter. All right. This also comes in head. V1 square plus Z1 is also you have seen in meter, and this P upon rho g as H is equal to P1 minus P2 upon rho g. This is also a unit of head. Head is in meter. All right. Bernoulli equation. And then we have the Venturi meter. Venturimeter, I've already explained you that it works on the principle of the Bernoulli equation, and this charge is A1 A2 root of 2g h upon root of A1 square minus of A2 square. This is the ideal discharge. If we multiply it by CD, this is the actual discharge. H is basically the height which is rising up or fall in the manometric tube, and we can also form this value P1 minus P2 upon rho g. All right, then we have last relation between coefficient. This is coefficient of discharge Cc into C. So these are all the formulas. And in terms of gate, what I recommend is you simply remember the formulas and make a notebook in which you can write the formulas, so that before I also have my own notebook while I used to prepare for the gate exam. You simply need to remember the concept and the formulas. That's it. You can neglect the derivation part to some extent, but you should know how the things are coming. For example, this part h, how it came. If I simply tell you this h, then you won't able, h is in meter, and suppose the question is being asked in terms of pressure, you won't able to solve it. So basically, in terms of gate, you need to remember the formula part. Simply remember the formula, solve more and more question as much as possible. Then you are good to go in gate. Then this is the first question which was asked in gate 2022 axi branch. Which of the following regarding Venturi meter is are correct? This is a multiple selective question MSQ. So the let's read the option. Option A, in the direction of flow, it consists of a converging section, a throat, and a diverging section. Is it true? First of all, it consists of a converging section, then a throat in which the diameter remains constant, as I told you, and then a diverging section. Is it true? Yes, it is true. है ना? Then we have in the direction flow, they have reversed the question, diverging section, throat. No, this is not true. First of all, we have converging section, then throat, then diverging section. So option A is correct. Option A is correct. Then next, because it's an MSQ question, you have to read the entire question. Option C is it is used for flow measurement at a very low Reynolds number. No, it is not being mentioned anywhere whether it is a look for low Reynolds number or for a high Reynolds number. Then pressure tappings are provided just upstream of the venturimeter and at the throat. Yes, this is correct. Pressure tapping are required because it is used to calculate the value of H. So option A and D are correct, isn't it? So you can see this part. First, there is converging section, then throat, then diverging section. Then they are pressure tapping, obviously, at this section P1 and P2. Why? To calculate the difference H in elevation so that we can calculate the value of discharge. So for this question, option A and D are correct. Option A and D are correct. So simple question. Next question. This question was asked in GATE 2021 AXI in your branch. Read the question. Water is flowing through a flow rate Q in a horizontal circular pipe. Okay. Due to the low pressure created at the Venturi section 1 in the figure. Section 1, yeah. There's a low pressure created at this section. Water from a reservoir is drawing upward using a connecting pipe. See, this is the reservoir and this is the pipe. Due to the low pressure at this section, this starts sucking this fluid upward. The flow at acceleration g, flow rate we have given q, d1 is this, d2 is this. The maximum height of the venturi from the reservoir sufficient to raise the liquid up to section. What is the height? What is this height which is required to raise by the this venturimeter so that the water from this reservoir reaches at this level? Why, first of all, the question is why there will be the flow from the reservoir in the upward direction. Since we all want to work in a low pressure zone, all right, you also don't want pressure in your life, so we all want to go toward the low pressure zone where there's a relaxation, we can easily good going life. So this fluid also have the same tendency. Due to the low pressure at this section, this fluid which is having a high pressure in this reservoir tend to move upward because it wants a relaxation life, it wants a peaceful life to have a low pressure. How to solve such question? Since we have discharge D1, D2 also is there. We can also apply Bernoulli equation at this point. At this section, at section 1, and at this section, at section 2. Or we can say at this section also. Yes, at section 1 and section 2, we can easily apply Bernoulli equation. So what was the Bernoulli equation? Again repeating the same thing. P1 upon rho g, P1 square upon 2g equal to plus of Z1 is equal to P2 upon rho g plus V2 square upon 2g plus of Z2. Alright. So what is happening at this section, section 1 and section 2? We are applying Bernoulli equation. We have diameter D1, diameter D2 here. So, alright. So this H arise. Why is this H is taking place? Arise is taking place. This is due to pressure difference, as I already told you. So here there's the atmospheric pressure. Here there will be some of pressure. I don't know which is P1. So what I told you, H rise is P1 minus P2 upon rho g. Remember this portion. And also one thing more, P2 is basically here the pressure at I'm talking about this section only. P2 is basically the atmospheric pressure. We can neglect as P2 because we are talking in terms of gauge pressure. So H is basically P1 upon rho g. So if you know this H, which is being asked, if you know this pressure P1 upon rho g value, we can easily calculate the value of H. So let's solve. At section 1, at section 1 and at section 2, we can see this data remains same because this is the same flow rate. So Z1 is cancelled. So we can write P1 upon rho g plus V1 square upon 2g equal to P2 upon rho g plus V2 square upon 2g. Sorry. Yes. So we have applied the Bernoulli equation. We can write it as uh, P1 minus P2 upon rho g is equal to 1 upon 2g P2 square minus of V1 square. Since P2 is atmospheric pressure, this is the atmospheric pressure, we can neglect it. 0. P1 upon Vg is equal to 1 upon 2g V2 square minus of V1 square. We can easily find the value of V2 and V1. Right? How? So discharge Q is equal to area into velocity. We have area A1. We have discharge remains constant. This is the velocity V1. We can find V is equal to Q upon A1. Discharge is given as, okay, we can first of all solving area is pi by 4 into d1 square. We can write it as 4q upon pi d1 square. Remember directly this thing, it will be easy for you. 4 into discharge q is 0.1 upon pi by 4 into diameter square. Diameter d1 is 0.8 centimeter. Please remember, please try to consider the units in mind before actually solving the question. 8 centimeter means in meter we need to convert because velocity comes out to be meter per second. All right, and we have taken this as also in meter cube per second. So 0.8 centimeter is 0.08 square And I hope everyone is having the Gate virtual calculator in their phone. If you don't have the Gate virtual calculator, please download it from the Play Store and try to solve all questions on that only, because it will be easier to solve question that virtual calculator. And if you don't know how to solve question in virtual calculator, do let me know. I will definitely explaining you how to solve question using the virtual calculator. What are the tips and tricks we can use to optimize our time in the actual examination. So if we solve this question, this value V1 come out to be Q upon A1 is 3.18 meter per second. All right. Then similarly, V2 is equal to Q upon A2. Simply put the values, and we will getting this value as 19.89 meter per second. So we have now V1, we have now V2. Simply put both these values here. Then P1 upon rho g is equal to P1 upon rho g is basically height, है ना? P1 is basically height. 1 upon Tg, 2g, sorry, 2g. V2 square is 19.89 square minus 3.18 square. So it comes, height comes out to be 19.6 meter. 19.6. So this is the value of height, and the gate has given the range of the value. You can see as 18.5 to 20. 18.5 to 20. So before one more thing, while you solve the question, please try to answer in up to 3 decimal places, because otherwise sometimes the answer may go beyond the range also. So for example, if you are getting your answer as 19.567, so don't write it as 19.5. Consider it to be 19.567 only, up to 3 decimal places. All right. So this is the answer for this question. Then the last question we have for today is venturimeter. Mm, hmm. Venturimeter with 75 mm diameter. Throat is placed in a 150 mm diameter pipeline carrying water. Pressure drop between the upstream and this is this. Find the flow rate. We have two methods to solve this question. One is to simply apply the formula Q A1 A2 root of 2GH on root of A1 square minus A2 square, right? And we have diameter D1, that is area we can easily calculate A1. A2 we can easily calculate, we have diameter D2. And so the only G we already know, the only thing which is disturbing us is the H. So we can find the value of H. I already told you it is the height due to pressure difference within the mercury column. H is basically P1 minus P2 upon rho G. So the pressure drop between the upstream and the tap is basically 40 kilopascal. So this is the pressure difference. Del P is 40 kPa. Then 40. Please convert it into Pascal. Remember the unit, please. Rho density is, if you are talking about water, density is 10 raised to power 3. If you have virtual calculator, please try to put values 9.81. Then H will come out to be around 4 meter. Around 4 meter. Right. Then simply put the values A1 A2 root of 2gs. A1 we can find by formula pi by 4 of D1 square. A2 is pi by 4 of D2 square. Alright. Simply calculate the value of A1 comes out to be, I think, 7.74. And A2 comes, sorry, A1 comes out to be A1 comes out to be 0.0176, and A2 comes out to be 0.0044. Simply put the value of discharge A1 and A2, and you will get the value of discharge as 0.4 meter cube per second. Is the answer. This was asked in Gate 2022 Axis. I hope this lecture is clear to you and you have understand the all points. Most important thing what you have seen is we have only three equation: continuity equation, Bernoulli equation, and we are solving question from that only. And you have seen the three consecutive paper 2020, 2021, 2022 also. The question are being asked from the formula part also only. So all you need is to remember the formula and to apply question and practice as much as possible as you can for the gate and try to solve question in virtual calculator. You can download it in Play Store from Play Store and let me show you. I don't know whether it's visible or not. This is the gate virtual calculator. This is the gate virtual calculator. You simply all you need is start calculator. You can download this from the Play Store. This is the application part. So the similar interface you will see in the actual examination. So try to solve the question in this only because it the interface of this gate virtual calculator is different from the normal calculator which we use. All right. So thank you so much for watching the video and thank you.